All right, everyone. Hello and welcome back to Calculus 1 video lectures. In this section, we are going to actually be going back to limits into another limit technique, which is called L'Hopital's rule. I know that the subtitles are not going to be able to correctly transcribe the name of this rule because it is named after the mathematician who came up with this method, but this section is going to be all about using L'Hopital's rule to find limits. Come on, there we go. So, to kind of refresh your memory, we have what are called indeterminate forms. And the indeterminate forms that we have covered so far are the 0 over 0 and infinity over infinity. 0 over 0 and infinity over infinity do not equal 1. They are indeterminate forms, and the last time that we covered these, I said at the time that there was a very limited number of techniques that you could use to deal with these two forms just with the resources at your disposal. For 0 over 0, all you had were factoring and rationalizing, and all you had for infinity over infinity was dividing top and bottom by the highest power of x. Starting in this section, you guys are going to be able to use what is called L'Hopital's rule to deal with these indeterminate forms. However, 0 over 0 and infinity over infinity are not the only indeterminate forms that there are. There are other indeterminate forms, which I have put in this other column, which I have labeled as more severe. The reason that these indeterminate forms are labeled as more severe is because they are not eligible to use what is called L'Hopital's rule. So 0 times infinity is not 0. The rule where 0 times anything is 0 doesn't apply here because infinity is not a number. Infinity minus infinity is another indeterminate form, and it does not equal 0 because infinity is not a number. And 0 to the power 0, 1 to the power infinity, and infinity to the power 0 are all indeterminate forms because mostly infinity is not a number. So, what does it mean for an indeterminate form to be classified, in my opinion, as more severe? So the 0 over 0 and infinity over infinity forms are easier to work with because if you have a limit that comes out to 0 over 0 or infinity over infinity, you can use what is called L'Hopital's rule to evaluate them. They are eligible for you to use L'Hopital's rule. The other indeterminate forms in the more severe column are not eligible to use L'Hopital's rule, and therefore you cannot use L'Hopital's rule when a limit comes out to any of those other indeterminate forms. So here's what L'Hopital's rule says. L'Hopital's rule is dealing with limits. So if you take the limit as x approaches whatever c of some function f of x divided by g of x. And the limit with just direct substitution comes out to either 0 over 0 or infinity over infinity. Then, a technique that you can use to evaluate it is to simply take the derivative of the top function and the derivative of the bottom function. Now, L'Hopital's rule is not used for taking derivatives. We are not taking the derivative of a quotient here. Remember, the derivative of a quotient requires you to use quotient rule. This rule uses derivatives as a tool in order to take regular limits. So if you have a limit that comes out to 0 over 0 or infinity over infinity, you can just take the derivative of the top function and the derivative of the bottom function and direct substitute again. Now the key with this rule is that it must be in one of those two forms. It must be either in the form of 0 over 0 or infinity over infinity. If direct substitution gives you a limit that comes out to any of those other indeterminate forms that were listed a couple slides ago, you cannot use L'Hopital's rule. So it must come out to either 0 over 0 or infinity over infinity. So just like any other limit, you should always start by direct substitution. And now more than ever, it is extremely important that you use direct substitution first, because you have to make sure that if it is indeterminate, that it is actually eligible for L'Hopital's rule. You must make sure that it comes out to 0 over 0 or infinity over infinity before you start taking any derivatives. So if you direct substitute 1 into the numerator, you get 1 plus 1 minus 2, which is 0, over 1 minus 1, which is 0. Because you get 0 over 0, it is eligible for L'Hopital's rule, which I'm going to abbreviate as L'H. So here's what L'Hopital's rule entails. What I'm going to do is I am going to take the derivative of the top function and the derivative of the bottom function. I don't need quotient rule because I'm not actually finding the derivative of a quotient. I'm just using derivatives to evaluate this limit. So if you take the derivative of the top function, you get 3x squared plus 2x minus 2. Then if you take the derivative of the bottom function, you get 1. Then, once you use L'Hopital's rule, you should try direct substitution again. So when we direct substitute, we get 3 times 1 squared plus 2 times 1 minus 2, which comes out to the real number 3. As soon as direct substitution yields a real number or something that is not indeterminate, then you are done. So L'Hopital's rule is really easy to use, and it can work on any limit where initial direct substitution gives you either 0 over 0 or infinity over infinity, no matter how bad it looks. So with this next limit, we should always try direct substitution first. So if you direct substitute, you get 9 plus 0, 0, which is 9. Square root of 9 is 3, minus 3 is 0, over 0. So because you get 0 over 0, you can use L'Hopital's rule. So for L'Hopital's rule, I'm going to have the limit as x approaches 0. And I'm going to take the derivative of the top and the derivative of the bottom, keeping in mind that this square root here can be written as an exponent of 1/2. So the square root of 9 plus 3x will require the chain rule, with the square root being the outside function and 9 plus 3x being the inside function. So taking the derivative of the outside, we're going to have 1/2 times the inside left alone, 9 plus 3x, and then decrease the power by 1, negative 1/2. Then we're going to multiply it by the derivative of the inside. Derivative of 9 plus 3x is 3. Then we're going to take the derivative of the bottom. Derivative of x is 1. Then, once you use L'Hopital's rule, you should try direct substitution again and see what happens. So 1/2 times 3 is 3/2. And then I'm going to direct substitute 0 in for x. So we have 9 plus 3 times 0 to the power of negative 1/2. And when you do all of the calculating, you get 1/2. Since your limit came out to the real number 1/2, let's try that again. That is going to be your final answer. So we're going to do that again for here. Remember, anytime you are faced with a limit, you should always direct substitute. Make sure that you can actually use L'Hopital's rule before you go using L'Hopital's rule. So if you direct substitute 0, you get e to the 0, which is 1, minus 0 minus 1, which is 0, divided by 0 squared, which is 0. So we can use L'Hopital's rule for this. So what I'm going to do is I'm going to come over here. I'm going to have the limit as x approaches 0, and I'm going to take the derivative of the top and the derivative of the bottom. So for the derivative of the top, the derivative of e to the x is itself. Derivative of minus x is minus 1. And then the derivative of x squared is 2x. Immediately after using L'Hopital's rule, you should always try direct substitution again. So if you direct substitute, here's what you get. You get e to the 0, which is 1, minus 1, which is 0, over 2 times 0, which is 0. So this is not a real number. Remember, this is another indeterminate form. And Because the indeterminate form is still 0 over 0, this limit is still eligible for L'Hopital's rule. So even if the direct substitution yields 0 over 0, that still remains eligible for L'Hopital's rule, so you can actually use L'Hopital's rule again. So using L'Hopital's rule a second time, you're going to go from the limit that you just had, the e to the x minus 1 over 2x, and we're going to take that limit and we are now going to take the derivative of the top function again and the derivative of the bottom function again. So derivative of e to the x is itself, derivative of minus 1 goes to 0, and derivative of 2x is 2. Then once you use L'Hopital's rule, you should direct substitute again, so e to the 0, which is 1, over 2. Now that you finally have a real number, now that your limit has come out to the real number 1/2, you are done. And L'Hopital's rule can be used for any limit as long as initial direct substitution gives you 0 over 0 or infinity over infinity. So if you take a look at this, the limit as x approaches 0 of e to the 3x minus 1 over sine x, try direct substitution. So we'll get e to the 0 minus 1, which is 0, over the sine of 0, which is 0. So because it comes out to 0 over 0, we can use L'Hopital's rule. So using L'Hopital's rule, we have the limit as x approaches 0. We're going to take the derivative of the top function and the derivative of the bottom function. So derivative of e to the 3x will require the chain rule. Exponential of base e is the outside function. The 3x is the inside function. So derivative of the outside is itself e to the 3x times derivative of the inside, which is 3. Then for the derivative of the bottom, derivative of sine x is cosine x. Then as soon as you use L'Hopital's rule, you should try direct substitution again. So you get 3 times e to the power 0 over the cosine of 0, which gives you 3 over 1, which is 3. So for this next one, keep in mind, anytime you take a limit, use direct substitution first. So direct substituting 0 into the top, we get 2 times the sine of 0 minus the sine of 0, which is 0, divided by 0 minus the sine of 0, which is 0. So you do get 0 over 0 for this. So because you get 0 over 0, we are allowed to use L'Hopital's rule. So we're going to go ahead and use L'Hopital's rule for this. So if we take the derivative of the top function, derivative of sine is cosine, so we get 2 cosine x. And then for the derivative of sine of 2x is going to be 2 cosine of x. Divided by derivative of x is 1, minus derivative of sine x is cosine x. Then as soon as you use L'Hopital's rule, you should do direct substitution. However, when you use direct substitution, you get 2 times the cosine of 0, minus 2 times the cosine of 0, sorry, this is cosine of 2x, which is 0, over 1 minus the cosine of 0, which is 0. So again, we have an indeterminate form, but it is still 0 over 0, so we can still use L'Hopital's rule. So we're just going to use L'Hopital's rule a second time. So we've got the limit as x approaches 0. We're going to take the derivative of the top again and the derivative of the bottom again. So for the derivative of 2 cosine x is going to be negative 2 sine x. Sorry about that. It is going to be negative 2 times the sine of x. Minus 2 plus 2 times 2 is 4. Negative times a negative is a positive. Derivative of cosine is negative sine, so 4 sine of 2x. All over, derivative of 1 is 0. Derivative of minus cosine x is positive sine x. So once you use L'Hopital's rule, you should use direct substitution again. So we have 2 times the sine of 0, which is 0, plus 4 times the sine of 0 is 0, over the sine of 0, which is 0. So once again, we direct substituted and we got 0 over 0. Keep in mind that as long as the limit still comes out to 0 over 0 or infinity over infinity, you can use L'Hopital's rule as many times as you need until you actually get a real number. And I promise that any question that involves L'Hopital's rule that you would ever get on a homework or exam, this does eventually stop. And 3, maybe 4 times at the most, you'll have to use L'Hopital's rule. So let's use L'Hopital's rule a third time. So we've got the limit as x approaches 0 of derivative of negative 2 sine x is negative 2 cosine x. Then derivative of 4 sine of 2x is going to be 8 sine of 2x. All divided by the derivative of sine x is cosine x. Then when you direct substitute again, you get negative 2 times the cosine of 0 plus 8 times the sine of 0, all divided by the cosine of 0, which when you compute this, you actually get the real number 6. So now that our limit has finally come out to a real number, we do not have to use L'Hopital's rule again. We are actually finished. So L'Hopital's rule is really easy to use as long as direct substitution initially yields 0 over 0 or infinity over infinity. However, as soon as direct substitution gives you one of the other indeterminate forms, you cannot use L'Hopital's rule. So the general idea with those is to manipulate the function using rules of algebra to rewrite it in such a way that an initial direct substitution will give you 0 over 0 or infinity over infinity. So if you do direct substitution for this problem, you get infinity squared, which is infinity, times the sine of 1 over infinity, which is 0. Sine of 0 is 0. So this is the infinity times 0 variety. And the strategy that I'm about to outline for you will work for pretty much any 0 times infinity indeterminate forms. So this would be a lot easier to work with, and we could actually use L'Hopital's rule if we actually had a quotient. If we had a quotient of 2 functions, maybe a direct substitution would give you 0 over 0 or infinity over infinity. So here's what I'm going to do with this. I have an algebraic part of this product, and I have a trigonometric part of this product. I'm going to take the algebraic part of the product, the x squared, and here's what I'm going to do with it. I am going to take the reciprocal of x squared, and I am going to put it in the denominator. You can do this because you're not actually changing the function. You're just unsimplifying it. You're undoing simplifying, and you're writing it in a very unsimplified form. So this doesn't actually change the problem, because if you were to then simplify this, you would go back to the original function. However, if you write it like this, here's what happens when you do a direct substitution. Remember that 1 over a really large number, infinity, is approximately equal to 0. So in the numerator, 1 over infinity will be 0. Sine of 0 is 0. Over 1 over infinity is approximately 0. So by taking the algebraic part of the product, taking its reciprocal and putting it in the denominator, we have now written this in a form where we can use L'Hopital's rule. So now that it is in the 0 over 0 form, now we can use L'Hopital's rule and take the derivative of the top and the derivative of the bottom. Keep in mind that 1 over x squared, if you can rewrite that as x to the power of negative 2, and you can take the derivative using power rule. So we've got the limit as x approaches infinity of the top function is going to require chain rule, so derivative of the outside function sine is cosine of the inside left alone. Then if you were to rewrite 1 over 4x squared as 1/4 x to the power of negative 2, for the derivative of the inside you will get 1/4 times, let's use the power rule, move down the power and decrease the power by 1. Then for the derivative of the bottom, again, if you rewrite 1 over x squared as x to the power of negative 2, you can use the power rule, so we're going to move down the power and decrease the power by 1. Then we're going to simplify this as much as possible. So negative 2 divided by negative 2 is going to cancel out. And the x to the power of negative 3 is also going to cancel out. So that will give us the limit as x approaches infinity of cosine of 1 over 4x squared times 1/4. So if you were to direct substitute infinity, remember 1 over a really large number is a really small number, approximately 0. So you'll get the cosine of 0 times 1/4, which gives you a final limit of 1/4. As soon as your limit comes out to a real number, you are done. So your limit is equal to 1/4. So that is going to be the general strategy whenever we run into the 0 times infinity indeterminate form. You're going to find the algebraic part of the product, take its reciprocal, and put it in the denominator. Once you do that, an initial direct substitution should give you either 0 over 0 or infinity over infinity. This is another example of a 0 times infinity. So if you direct substitute 0, you get 0 times the limit at, natural log is going to approach negative infinity as x approaches 0 from the right. So it doesn't matter if it's negative infinity or positive infinity. This is still the 0 times infinity indeterminate form. So what we're going to do with this is we're going to take the algebraic part of the product. We are going to take its reciprocal, and we are going to put it in the denominator. So here's what that will look like when we do that. The reciprocal of x is going to be 1 over x, and I'm going to put that in the denominator. Then that natural log of x I'm going to leave in the numerator. So now that you have rewritten this, you should try direct substitution again and see if you actually get 0 over 0 or infinity over infinity. So the limit as x approaches 0 of natural log of x is going to be infinity. Over 1 over 0 is approximately infinity, because remember, 1 over a really, really tiny number 0 is a really, really big number, approximately infinity. So 1 over 0 is approximated as infinity. So now that direct substitution gave us infinity over infinity, we can use L'Hopital's rule. So now let's go take the derivative of the top and the derivative of the bottom. So we've got the limit as x approaches 0 from the right of derivative of natural log x is 1 over x. Then for the derivative of 1 over x, remember 1 over x can be rewritten as x to the power of negative 1, which would allow you to use power rule. So just rewriting 1 over x as x to the negative 1, I'm going to move down the power, and then I'm going to decrease the power by 1. So you get negative 1 times x to the power of negative 2. Then let's do some simplifying, because this is kind of a mess, so let's simplify it. So if you rewrite the numerator as x to the power of negative 1, what you can do with this is, since you have a division of two exponential expressions with the same base, you can simplify it by subtracting their powers. So if you subtract their powers, top exponent minus bottom exponent, you will get negative 1 minus negative 2, which will give you positive 1. So now that we have simplified this, we are now going to take the limit as x approaches 0 from the right, and we're just going to direct substitute 0. So we'll get negative 0, which is 0. Yes, you can have a limit come out to 0. 0 is a real number, so your final limit is equal to 0. Now, we're going to go through all of the other indeterminate forms and go through the general strategies that we use for them. So we've covered the 0 times infinity. You would take the algebraic part of the product, reciprocate it, and put it in the denominator. Infinity minus infinity, unfortunately, does need to be handled on a case-by-case basis, because there are a number of different types of functions that could give you the infinity minus infinity indeterminate form. So we're going to look at a couple of the more common ones. So for this one, if you direct substitute infinity, you get infinity minus infinity. The reason that the infinity minus infinity is happening is because on either side of that subtraction, you have two different terms, both with x in them. So the 0 times infinity is really easy to deal with because if you have that product, you can reciprocate one of the parts of the product and put it in the denominator. So here's what we're going to try and do with this. We are going to try and factor out some sort of common factor. We're going to try and find a common factor, and we are going to factor it out because on either side of that central minus sign, both of these terms have an x in it, which is kind of causing the infinity minus infinity. So if we could somehow factor out a greatest common factor of x, we could rewrite it as a product, and then we have a strategy that is really easy to use for products. So the first thing that you'll notice is that inside the square root there is an x squared. However, because of this minus sign right there, you cannot just take the square root of x squared and the square root of 3x. You cannot break up addition or subtraction inside of a square root. So do not break those up. So at the moment, you cannot take the square root of x squared and just cancel those out. However, if you could somehow rewrite x squared minus 3x as some sort of product, you can break up products underneath a square root. So here's what I'm going to do with that square root first. I would really like to take the square root of that x squared. The only way I would be able to take that square root of that x squared and cancel those out is if the x squared was written as a product. So I am going to force there to be a common factor of x squared between x squared and minus 3x. It might sound like I'm cheating, but as long as you follow all of the same rules for when you factor out a greatest common factor, you can force there to be a common factor of x squared where there really isn't any. So remember, when you factor out a variable, what you're going to do is you're going to subtract each of the existing powers by the power of that common factor that you took out. So I'm going to take both of those terms inside the square root, and I'm going to subtract both of their powers by 2. So here's what happens when we do that. We get x squared, when we take an x squared out of x squared, we are left with 1. Leave the minus 3 alone, and then 1 minus 2 will give us x to the power of negative 1. So, okay, we got a negative power inside the square root. That's not going to be a big deal. The big thing is we now have a product inside of that square root. You are allowed to break up products inside of square roots. So what I'm going to do is I'm going to split apart that square root into the square root of x squared times the square root of 1 minus 3 over x. The square root of x squared, so the square root and the square can now cancel each other out, giving you the limit as x approaches infinity of x minus x times the square root of 1 minus 3 over x. Now, if you take a look on either side of this central minus sign, both of these terms now have a common factor of x, so I'm going to factor out the x, which was the whole point of doing this. So we have the limit as x approaches infinity of x times 1 minus the square root of 1 minus 3 over x. Now that we have it written as a product, we probably have a different indeterminate form. So at this point, now that we've done all of that simplifying, we should try direct substitution again and see what we get. So if we direct substitute infinity, we get infinity times 1 minus the square root of 1 minus 3 over infinity. Remember, 3 over infinity is 0. 1 minus 1 is 0. So now this is the 1 over 0 the 0 times infinity indeterminate form. It's still not eligible for L'Hopital's rule, but we now have a strategy to deal with this. So just like the other 0 times infinity problems, you're going to take the algebraic part of the product, the easier part of the product, x. I'm going to take its reciprocal, and I'm going to put it in the denominator. So I'm going to take the reciprocal of x, and I'm going to put it in the denominator. And everything else, that other part of that product, I'm just going to leave alone. So 1 minus the square root of 1 minus 3 over x. Then, as soon as you rewrite it in this form, try direct substitution again, remembering that 1 over infinity is a really, really small number, approximately 0. So we get 1 minus the square root of 1 minus 0, which is 0, over 1 over infinity, which is 0. So now that we have finally written this in a form that gives us 0 over 0 when we direct substitute, we can finally use L'Hopital's rule. So when we use L'Hopital's rule, we're going to take the limit of the top function and the limit of the bottom function. Limit of the top will require some chain rule. So derivative of 1 is 0, leave the minus sign there. If you rewrite the square root as an exponent of 1/2, this is going to require the chain rule. So derivative of the outside, 1/2, leave the inside alone. And then decrease the power by 1, so we get negative 1/2. Then if you multiply it by the derivative of the inside, keep in mind that 3 over x can be rewritten as 3x to the power of negative 1, which would allow you to use power rule. So we've got this existing negative here, derivative of 1 is 0. Then the derivative of 3 times x to the power of negative 1 will be negative 3 times x to the power of, decrease the power by 1, negative 2. Then in the denominator, derivative of x to the power of negative 1 is going to be negative x to the power of negative 2. And then for simplifying, remember that you can cancel out common factors across multiplication. So first of all, the negative times a negative will give us a positive. Negative divided by a negative will give us a positive. And then the x to the power of negative 2 can cancel with this, x to the power of negative 2. So when you direct substitute infinity, 3 times 1/2 is going to be 3/2 times 1 minus 3 over infinity to the power of negative 1/2. Remember that 3 over infinity is approximately 0. 1 minus 0 is 0 to the power of negative 1/2 times 3/2 is 3/2. So now that your limit has come out to the real number 3/2, that you are done and your limit is equal to 3/2. Now here's another common instance that can give you an indeterminate form of infinity minus infinity. So in this case, we have two separate fractions that are each coming out to infinity. So, the 1 over the natural log of 1 is going to be 0. 1 over 0 is approximately infinity. Minus 1 over 0 is approximately infinity. So remember, 1 over a really, really tiny number 0 is a really, really big number, approximately infinity. So the two separate fractions are the reason that this is giving us infinity over infinity, because each fraction individually is coming out to infinity with direct substitution, and because they are being subtracted, we get infinity minus infinity, which is indeterminate. Remember, since infinity is not a number, it's a concept, infinity minus infinity does not equal 0. So here's what we're going to do with this. This would be a lot easier to deal with if this was only in one fraction, because remember, infinity over infinity and 0 over 0 are eligible for L'Hopital's rule. So if I could combine these two fractions into one fraction, I would probably get this into a form that is eligible for L'Hopital's rule. So that's exactly what I'm going to do. I'm going to find common denominators between these two fractions, and I am going to combine them into one fraction. So the common denominator, they don't have any common factors, so I'm just going to simply take 1 over the natural log of x, and I'm going to multiply both the top and the bottom by the other fraction's denominator, x minus 1. Then I'm going to do the same thing over here. I'm going to take this 1 over x minus 1, and I'm going to multiply both the top and the bottom by the natural log of x. Then, now that we have our common denominator, we are just going to simply subtract the numerators. So the limit as x approaches 1 from the right of our common denominator is going to be natural log of x times x minus 1 all over x minus 1 minus natural log of x. So now that you have combined these into one fraction, you should try direct substitution again and see what happens. So if you direct substitute 1, you get 1 minus natural log of 1, which is 0, over natural log of 1, which is 0, times 1 minus 1, which is 0. So now that we have finally written this so that we get 0 over 0 with direct substitution, we are going to use L'Hopital's rule. So using L'Hopital's rule, I have the limit as x approaches 1 from the right. Let's take the limit of the top function. So the derivative of the top function. So derivative of x is 1, derivative of minus 1 is 0, derivative of natural log x is 1 over x. Then for the derivative of the bottom, it really doesn't matter if you distribute natural log or not. You're going to have to use product rule regardless. So for the derivative of the bottom, natural log x is the first part of the product and x minus 1 is the second part of the product. So derivative of the first part of the product, derivative of natural log of x is 1 over x, times the second part of the product left alone, plus the first part of the product left alone, times derivative of the second part of the product, derivative of x minus 1 is 1. And then I'm going to at least attempt to do a little bit of simplifying here, and then I'm going to try direct substitution again and see what we get. So we got the limit as x approaches 1 from the right of, the numerator is not going to simplify, so we have 1 minus 1 over x. Then in the denominator, I'm just going to distribute that 1 over x, so 1 over x times x is going to give us 1. And then that'll give us minus 1 over x plus the natural log of x. Then as soon as we simplify, we're going to try direct substitution again. So if you do direct substitution, we get 1 minus 1, which is 0, over 1 minus 1 plus natural log of 1 is 0. So remember, even if another direct substitution gives you 0 over 0, as long as it continues to be 0 over 0, we can just simply use L'Hopital's rule again. So using L'Hopital's rule again, we're going to take the derivative of the top function and the derivative of the bottom function. Keeping in mind that 1 over x can be rewritten as x to the power of negative 1, and you can use power rule. So let's take the derivative of the top. So derivative of 1 is 0. And then we have minus derivative of 1 over x is going to be negative 1 times x to the power of negative 2. Then for the derivative of the bottom, derivative of 1 is 0. Derivative of 1 over x is going to be negative 1 times x to the power of negative 2. Then plus the derivative of natural log of x is going to be 1 over x. So when we simplify this, we've got a lot of double negatives here. Negative times a negative is a positive 1 over x squared. It doesn't really matter if you leave it as x to the negative 2 or rewrite it as 1 over x squared. I prefer writing it as 1 over x squared, especially if we're dealing with infinities, but that is up to you. Then in the denominator, negative times a negative is a positive 1 over x squared plus 1 over x. Then once you simplify, you should direct substitute again. So when you direct substitute 1, you get 1 over 1 plus 1, which gives us a final limit of 1/2. So 1/2 is now your final answer. So infinity minus infinity, while it's handled on a case-by-case basis, these are the two general strategies that you will use in the two general kind of scenarios that would give you an infinity minus infinity. So you're either going to find a greatest common factor and factor it out, or you're going to take two separate fractions, find common denominators, and subtract them. For the other three indeterminate forms, because they all involve exponents, we're actually going to use the same strategy for all three of these. So for 1 to the power of infinity, 0 to the power 0, and infinity to the power 0, they're all going to use the same strategy. And what is causing the indeterminate form for all three of these is the funky base and exponent combination. So if we could get rid of that exponent somehow, we could probably write this in another indeterminate form that would be easier to work with. So to get whatever is causing the weird exponents out of the exponent, you use logs. So the core of this process is going to involve natural logs. Now remember, when we're rewriting functions, we cannot change the function. We're just doing a lot of algebraic manipulation that doesn't actually change anything, but just does some rewriting and doesn't actually change the problem. So what we're going to do first is we are going to take the natural log of the function. Then you're going to take whatever was in that exponent and you're going to use the power rule of exponents to rewrite it in front of the logarithm as multiplication. Then what that will probably give you is one of the 0 times infinity indeterminate forms. So you'll have to take some reciprocals and rewrite them in denominators to get this in the form of 0 over 0 or infinity over infinity. As soon as this is in the form of 0 over 0 or infinity over infinity, you can use L'Hopital's rule. And then you'll use L'Hopital's rule to actually find its limit. However, you can't just take the natural log and leave it like that. That would change the problem. So this final step, which takes 10 seconds, but it's really easy to forget about, you have to undo that natural log that you took at the beginning. Because as long as you undo whatever manipulating you did before, you didn't actually change the problem. So once you actually figure out the limit and get your limit, your final answer is actually going to be e to whatever that limit came out to. So let's say, that this limit came out to some number L. You're going to take that number and put it into an exponent of e. Then that will be your final answer and your final limit. Do not forget to do this because you can't just take a natural log and leave it like that. You have to undo it at the end of the problem by putting it in an exponent of e, and then that will undo it and you will be all set. So this next example is a 0 to the power 0 example. I think it's obvious when you look at it with direct substitution. So step number 1 is we are going to take this function and we are going to take its natural log. We will undo it later, but for now we're just going to take the natural log of this function. So we've got the natural log of x to the power x. Then anytime that you have an exponent inside of a logarithm, you can rewrite it in front of that logarithm as multiplication. So we're going to rewrite this as the limit as x approaches 0 from the right of x times the natural log of x. Now after any simplifying step, you should always try direct substitution just to see where you are and what you're dealing with. So if you direct substitute, you get 0 times the limit as x approaches 0 from the right of natural log x is negative infinity. This is the 0 times infinity indeterminate form. So we're going to use that same strategy that we used for any of the other 0 times infinity indeterminate forms. We're going to take the easy part of the product, mostly the algebraic part. We are going to take its reciprocal and we are going to put it in a denominator. So we have the limit as x approaches 0 from the right of the natural log of x over 1 over x. Then, after each simplifying step, try direct substitution again. So we get the limit as x approaches 0 from the right of natural log x is infinity. And then 1 over 0 is a really, really big number, approximately infinity. So now that it is finally in the form of infinity over infinity, let's use L'Hopital's rule to take this limit. So using L'Hopital's rule, we've got the limit as x approaches 0 from the right of derivative of natural log of x is 1 over x. Derivative of 1 over x is the same that it was before, which is negative 1 over x squared. Please simplify this because it's a mess, so you really should simplify it before you try direct substitution again. So doing some subtracting of exponents or flipping and multiplying, we've simplified this a couple of times already. This simplifies as negative x. Then when you direct substitute, you get 0. However, notice I did not circle that as my final answer. Your final answer is not 0. Because remember that natural log you took at the beginning of this problem? You have to undo it now so that you didn't actually change the function. So step number 2, all we are going to do is take that 0 and we're going to write it into an exponent of e, and then that will be our final answer. So this limit will be e to the 0, which is 1. And then 1, that is your final answer. So don't forget that last step. It doesn't take long, but whatever this number down here comes out to, you have to make sure that you put it in an exponent of e, and then that will be your final answer. And then for this last one, this is an example of a 1 to the power infinity indeterminate form. All of the indeterminate forms that involve weird base and exponent combinations are going to be handled in this exact same way. So the first thing that we are going to do is we are going to take the natural log of this function. So I'm going to have the natural log of 1 plus 1 over x to the power of x. Then I am going to take this exponent that is inside of the natural log, and I'm going to rewrite it in front as multiplication. So that will give us the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Then you should try direct substitution, see where you're at. So if you direct substitute infinity, you get infinity times natural log of 1 plus, remember 1 over infinity is 0, so natural log of 1 is 0. So this is now the infinity times 0 indeterminate form, which isn't as bad. So we're going to take the simple algebraic part of the product x. We're going to take its reciprocal, and then we are going to put it in the denominator. So this is what we will end up with. In the numerator, we'll have the natural log of 1 plus 1 over x. And then in the denominator, we will have 1 over x. So now that we've done this rewriting, we should just mentally direct substitute one more time to make sure that this is in a form that can use L'Hopital's rule before we dive into L'Hopital's rule. So in the numerator, we have the natural log of 1, which is 0, over 1 over infinity is approximately 0. So now that this is in the 0 over 0 indeterminate form, now we can use L'Hopital's rule, keeping in mind that 1 over x can be rewritten as x to the power of negative 1, and you can use the power rule. We've done this derivative several times now. So we've got the limit as x approaches infinity of the numerator is absolutely going to need the chain rule. So using the chain rule, the derivative of the outside is going to be 1 over the inside left alone, 1 plus 1 over x. Then we're going to multiply it by the derivative of the inside. So the derivative of 1 is 0. Derivative of 1 over x is going to be negative x to the power of negative 2. Then in the denominator, derivative of 1 over x is going to be negative x to the power of negative 2. Then when you simplify, the negative x to the power of negative 2's can cancel each other out, leaving you with the limit as x approaches infinity of 1 over 1 plus 1 over x. Then you should try direct substituting again, keeping in mind that 1 over infinity, 1 over a really large number is a really small number, approximately 0. So we have 1 over 1 plus 0, which is 1. Now, don't forget, for your final answer, you have to undo that natural log that you took at the beginning. So this limit is going to come out to e to the 1, which is e, and then that is your final answer. Don't forget this step. It is easy to forget, but if you forget this step, you will lose points, unfortunately. All right, so that was it for L'Hopital's rule. All of the questions on your homework will be in one of those indeterminate forms, and they're going to look very similar to the problems that were covered in this video. Now, since this is covered after the third exam, this material, along with everything else that we do from here on out, will be on the final exam in some capacity. So, I thank you all very much for watching, and I will see you in the next video.